Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So now you are in part 5, chapter number 2. So in this part, which is the final part of chapter number 1, we discuss about the efficiency of the compressor, where we will learn about various equation of efficiency for the compressor. Okay, about the compressor efficiency, before we discuss further about the compressor efficiency in terms of equation, let we discuss about the process and also the variable or parameter that involved during compression process for the compressor. So this figure shows the cross-section drawing of a gas turbine engine, where our focus now is about the compressor. So if we redraw more simplified schematic diagram, so you will get the second figures, where we can see here the inlet condition for the compressor is at state number 1, the outlet condition for the compressor at state number 2. So the process that involved for the compressor is the compression process, where we need to supply work in to the compressor so that the rotor of the compressor will rotate in order to suck the fresh air from the surrounding to go through the compression process in order to produce compressed air before entering the combustion chamber. So in order to describe the process, we need to refer to TS diagram, the diagram that we already learned in thermodynamic 2 about the Brayton cycle. So the process of the compression shown by this process, there are two types of process involved: the ideal process or the isentropic process, and also which is represented by a process start from state number 1 to state number 2s. The second process involved the actual compression process, start with state number 1 to state number 2a. So now, because we discussed about the turbomachinery, so all the device of a turbo machine involve with moving fluid flow through the device or through the rotor, through the blades. So we need to consider the term for kinetic energy of the fluid and also the velocity of the fluid at the inlet and also at the outlet. So that's why we need to know about the relationship between HS, that is represented by HS diagram. So in this diagram shows the parameter that involved during the compression process, where at the inlet and also at the outlet, so we need to consider two type of state: state number 1 static state and state number 2 stagnation state. Okay, which means every inlet and also outlet will have, in terms of pressure, two type of pressure. So at the inlet condition will have static pressure P1 and also stagnation pressure PO2. However, at the outlet of the compressor also will have two type of pressure need to involve: static pressure P2 and also stagnation pressure P02. So the state 1, state number 2 represent the static state. State number 01, 02 represents stagnation state, and state 02s represents stagnation state during isolate process, and state 2s represents static point during the isentropic process. And in this figure also we can see that the term or the parameter for velocity C1, C2 and also C2s, which represent the velocity of fluid at the inlet and also at the outlet respectively. So this velocity of the fluid contribute to the term for the kinetic energy of the fluid at the inlet and also at the outlet of the compressor. Okay, in terms of process, the vertical line shows the ideal process of the compression, and the other inclined lines represent the actual process of the compression. Okay, now if you want to determine the value of stagnation enthalpy, we can use this formula, where the stagnation enthalpy at the inlet is equal to H01 equal to H1 plus half C1 square. However, at the outlet of the compressor, the stagnation enthalpy H02 equal to H2 plus half C2 square. Okay, now we will discuss about the general equation for compressor efficiency. Okay, so this figure shows the single stage of compressor in a gas turbine engine. So if we just redraw the simplified schematic diagram for the compressor part, so we can see that the compressor will attach with a starter or with a electric motor. Okay, so the first general efficiency equation for the compressor is overall efficiency mu 0 or mu naught. So the power input to the rotor of the compressor is always less than the power supplied at the coupling because of external energy losses. So in order to explain this statement, so we need to refer to the schematic diagram of the compressor and also electric motor. So from the figure we can see that energy we supplied to the compressor by the electric motor or by the starter by the starter or by the turbine. Okay, that represented by the what I call pink color arrow. So due to the mechanical movement of the shaft and also of the the coupling, there will be energy losses throughout the process. So due to the energy losses, the energy that received by the compressor will be less than energy that's supplied by the motor. So through the compression process, there will be more energy losses due to the pressure drop, friction, heat loss to surrounding and so on. So the compressed air that produced from the compression process will have more or less energy if we compare to the energy that received by the compressor at the beginning of the process. So now the equation for overall efficiency for the compressor, mu 0 or mu naught equal to useful power input to fluid divided by power input to the coupling of shaft, where the power input to the coupling of the shaft actually refer to the amount of energy that's supplied by the electric motor or by the starter. And the useful power input to the fluid is actually refer to the energy that I call that received by the compressed air after the compression process. The second general efficiency for the compressor is the isentropic efficiency mu c, where the formula will be mu c equal to useful power input to the fluid divided by the power input to rotor. Okay, so the power input to rotor represented by the energy that shows by the green arrow in the diagram, and the useful power input to the fluid referred by the energy that represented by blue arrow. So if you combine both a formula of efficiency, which is overall efficiency, and also the isentropic efficiency, so we will get the mechanical efficiency mu m for the compressor, where the formula for mu m equal to mu naught divided by mu c. Okay, for the compressor, there will be the compressor efficiency expression based on the function of the compressor, similarly like the turbine. So the first expression in terms of efficiency for the compressor is total to total efficiency, which is mu tt, where this efficiency is the meaningful efficiency for an adiabatic compressor. So if you were asked to determine the efficiency of the compressor, so you need to refer to the total to total efficiency equation. However, for the compressor, if you compare to the turbine efficiency expression, for a compressor there is no total to static efficiency equation due to in a compressor the energy is fully utilized. All the compressed air ideally enter the combustion chamber for the combustion process. So that's why for the compressor efficiency, if you compare to the turbine, so there is no total to static efficiency for the compressor. So the compressor only have total to total efficiency, mu Tt. So the formula for total to total efficiency for the compressor, mu Tt equal to minimum adiabatic work input per unit time divided by actual adiabatic work input to rotor per unit time. So mu C or mu Tt equal to delta Wc minimum divided by delta Wc. So delta Wc minimum represent the amount of W work in during the ideal compression process, and delta Wc is what I call the work in during the actual compression process, which is also equal to the enthalpy difference during the ideal process, H02S minus H01 divided by the enthalpy difference during the actual compression process, H02 minus H01. So the ideal process, if we refer to HS diagram, represented by this blue color line, and the actual process of the compression represented by the red color line. So if we neglect the kinetic energy of the fluid, so we can ignore the term for kinetic energy in the stagnation enthalpy formula. So now for this condition, the stagnation enthalpy value will be equal to the static enthalpy value. So instead of we use stagnation enthalpy value, we can use static enthalpy value directly in the equation, where mu Tt for the compressor equal to H2S minus H1 divided by H2 minus H1. Okay, for this slide, I will summarize the formula for work, specific work done, and also the efficiency for turbine and also the compressor. So first, let me remind you that I will generalize the what I call the state condition and also the inlet condition and also the outlet condition for both turbine and also the compressor. So in this summary, so I will generalize the number of the inlet and also of the outlet. So number 1 will represent the inlet condition for both turbine and also compressor, and number 2 will represent the outlet condition for the turbine, also for the compressor. So throughout this slide, the equation will based on number 1 for the inlet, number 2 for the outlet. Okay, specific work done. If we base on the Euler equation, so we will get the formula for W out for the turbine, delta Wt equal to U1 C theta 1 minus U2 C theta 2 equal to H01 minus H02. However, for the compressor, the work input for the compressor equal to delta Wc equal to U2 C theta 2 minus U1 C theta 1 equal to H02 minus H01. If we base on the enthalpy difference formula, so we have two processes involved, the actual and also the ideal process. For the actual process, the work output for the turbine, delta Wt equal to H01 minus H02. For the compressor, delta Wc work in equal to H02 minus H01. For the ideal process, for the turbine, delta Wt maximum will be equal to H01 minus H02S. However, for the compressor, delta Wc minimum equal to H02S minus H01. So all this equation for the specific work done will use to generate the formula for the efficiency for both turbine and also compressor. For the turbine, General formula for efficiency is equal to delta WT divided by delta WT maximum. So delta WT is the work output during the actual expansion process. Delta WT maximum is the ideal, the what I call the work output during the ideal process. So for the turbine, there are three general equation for the efficiency. We have overall efficiency, isentropic efficiency for the turbine, and also the mechanical efficiency. So next, the special expression in terms of efficiency based on the function of the turbine. So we have two type of expression. First, total to static efficiency, which is equal to H01 minus H02 divided by H01 minus H2S. And the second expression is total to total efficiency, which is equal to H01 minus H02 divided by H01 minus H02S. For the compressor, general equation for efficiency equal to delta WC minimum divided by delta WC. Delta WC minimum actually is the work input during the ideal process of compression, and WC is work input during actual process of the compression. Similarly, we see the turbine. The compressor will have three general efficiency: overall efficiency, isentropic efficiency of the compressor, and also mechanical efficiency. If you compare the turbine, the compressor only have one efficiency expression based on the function of the compressor, which is referred to total efficiency, which is equal to H02S minus H01 divided by H02 minus H01. There will be no total to static efficiency for the compressor. Okay, so other than general efficiency formula, in order to determine the efficiency for the turbine and also for the compressor, so you can use the total to total efficiency formula for turbine, and also the what I call, and also the isentropic efficiency for the compressor will also represent by the total to total efficiency for the compressor. Okay, now to test your understanding about this topic, answer the question below. Okay, so if someone asks you to determine the efficiency of the compressor, which type of efficiency equation will you will choose, and explain why. So answer the question and submit. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic, and the clue also will be given in the link. Okay, that's all for chapter number 1. Assalamualaikum warahmatullahi wabarakatuh.